Hi there again. So let's move to the next tutorial 10. So far I hope you're having a blast. And in this tutorial 10, as I previously said, we're going to address the other correction that we need in turbulence modeling, which is related to curvature corrections. Curvature correction. So again, remember that you have documentation, and in theory also we address this, and in documentation you will have it here. So basically this curvature correction is related to system rotation and that vorticity that is generated when you have a lot of curvature. And not always you will need to use it. Very specific cases are required, like mixing cyclone generators and mixing tanks, stuff like that, and also winter vortices. We're going to work on that. But one of the questions is, people say, okay, when do I enable these actions, or why they are not always enabled? And remember that these are corrections that some cases that can improve, but some cases they can be detrimental to your solution. So that's why they are not always enabled. So my advice is just take the default options, know your physics well, and according to what you have, you might or might not need to enable those options. Sometimes you have experimental values, you will realize quite easy, okay, I will need to enable this correction. But let's say start and practice that. For instance, the correction related to the production is one correction that you usually use with transition to modeling, and this curvature correction also is a correction that you use when you have a strong vorticity, concentrated vortices like wind tips or mixing tanks, stuff like that we're going to see in these two cases. So there you have the theory. Okay, what is going on is usually is a damping function, okay, or a limiter. So following with this rule, it will start to limit the production. See here how it works. You have PK production, and now you have this limiter. So previously in production limiter you have this, or but probably more complicated, the cattle down there that you have explained. And here we have this limiter that you put it here to avoid that excessive production, okay, due to the curvature effect and system rotation. So here you have the explanation goes through that, but we addressed a little bit this in during the lectures. So you have here the case. This is a validation case. So here you can download the experimental data. Here you have the mesh. So here I will drive you how to do this setup. This is the second case that we're going to do later. And here you have this nice reference related to the curve channel. And basically this is a thesis, is an oldie, but it's a good one. Okay, so basically look at that. This is a geometry, small geometry, and we're going to do is just take we're not going to simulate everything. We're going to take a small section here, and we're going to compare with experimental results that we have all this data available here. You can extract it with this nice thesis. Okay, so see that I already have also another case that I have the whole stuff, okay, and I can measure. But for this case, we're not going to do this. Okay, let me close here. We're going to do this instead, a small section of that geometry. Okay, so we have a wedge here, and we're going to measure precisely there. So just go to your case and read your mesh. Okay, so this is the mesh that we have. So first I'm going to show you a few things when you read the mesh, and then I will open the predefined case where I have the boundary conditions. But the thing here, when you read this mesh, you will have this warning here. Okay, you might get worried, but remember, these are warnings. So get worried when you see error. But I know precisely what is this warning. So this mesh, when it was created, the cell sum was given this name solid. So when Fluent finds this solid name, it will say automatically, I will assign a solid material there. So this warning is kind of related to that. So what you need to do here is see that this is the name solid, and it's automatically selecting solid. So you put fluid, you will solve this problem. Assign air, and you are done. Okay, that problem should be taken care of with that. So be careful also when you're doing the mesh with this name, okay? So don't put also spaces or funny characters like question marks and stuff like that, or underscore at the end. That might give you problems here in boundary conditions, okay? But this first warning has been addressed with this modification. The next thing that I want to do before changing to the predefined case is that here we're going to use periodic boundary conditions, okay? So far here we have these two patches. So you go here, see that our mesh is defined. You have inlet, outlet, and the walls, okay? But we want to use periodic boundary conditions. So periodic boundary conditions means that, let me sketch a little bit here. Means that whatever is entering here is going out here, and whatever is going out here is entering here, okay? So kind of to simulate an infinite domain. So this is what we're going to do here, this periodic boundary condition, and this is what I want to show you. So this case also can be properly worked using inlet, outlet, but just to show you a new sense that it's very often, I'm not a big supporter of periodic boundary condition, but very often you find it. So to set up this one, you will see that you cannot access that boundary condition from here. So for instance, inlet, you will see that, okay, this one, you don't have it here. So you need to assign that one from the text user interface. So let's go into the text user interface, and to assign that periodic boundary condition, one thing that let's first go. So you have in the menu mesh, and then you have modify zones, as I would recall, and yes, I think make periodic. Okay, so this is the one that we're going to use. But before doing that, we need to know the IDs of these patches or these surfaces. So as you click here, see that you have this number, ID 14, ID 15, and all the others. So these IDs, you can do it to do many operations, okay, to modify the mesh. So for instance, here, I think somewhere you will have some options that you can do manipulations in those zones, okay, interface, everything. So you here zones. So you need to know that information, the ID of this zone. So let's do it periodic. So make periodic, and it will ask you the periodic zone. So I want first 14. You give the ID, and the ID of the second one, the shadow. So periodic and shadow, and then kind of you will connect these two zones topologically, okay? So what is going on in one is what is going on in here is entering in the other, and what is going on in the other is entering in the other. Okay, so if 15, here we'll ask you what kind of periodicity do you want. So you can have rotationally periodic, okay, or translationally periodic. So rotational is when you have angle like this, and translational is when you have a straight pipe, let's say. Okay, so here this is not translational, this is periodic. So yes, I want rotational, and then yes, create it, type again, and see that it's telling you zone 15 it was delete, but it was collapsed into the other one just to, it was not collapsed, it was like communicated with the other one to exchange information. So right click and see that now the color changed. But as you go here, now see that you have periodic. So you go inlet, this is the name that it was taken. This is the one you can change that name. You see that now it's periodic, and you can access that periodic there. So if you want to change it here, just click there. So as you type edit, you can change the type of periodicity if you want, but what is important that then you need to assign boundary conditions to this, okay? So as you go to periodic conditions, here you need to define, you can define the mass flow, or you can define the pressure gradient, okay? This is the flow direction. So here we're going to define the pressure gradient. So now that you have this, keep it open because I'm going to give you these values. Okay, we haven't done anything, but I will open the case that I have already set up. Okay, I don't recall everything, and I go here. So in my case, I already created periodicity. You have everything. Okay, see that I have the periodic. So let me go back here. So a standard pressure basis is steady. You go to viscous, enable the default model, which is K omega SST, and see that this is the default. Then later we're going to rerun enabling this option, okay? But just leave it default, nothing else. Materials, okay, materials, we are matching the conditions of the thesis. So you go to material and assign these values, which are not the standard one, okay. Probably I think we are going to get the same results using the standard one, I don't recall. But assign these values, okay, density and viscosity, you have them there. Okay, so we already changed here with the stuff when reading the mesh. Then cell zone, remember that here you can choose operating conditions, the defaults are okay. So here be sure to have fluid. And then boundary conditions. So you have top and bottom are these walls, there are walls. We need to define the conditions here in periodic conditions. So define this pressure gradient. So specify pressure gradient, this direction, and 70. So this values is chosen to match the condition of the thesis, okay? The mass flow, which I will recall is 1.5, okay? So it was 70. Nothing else to define here. Solution methods, again, steady simulations, best method ever, this one. But if you want to try something else, feel free. Then go controls, default controls, and reports. Okay, I will take some time here because we want to create the default report. So always I like to put y plus average top and bottom. So one thing that look at this is a very nice mesh, very fine mesh to the walls, always well resolving. And let me here mass flow. Okay, so this is here we're computing the mass flow at the inlet, so between both of them. Okay, so be careful that compute it directly when you compute. This case I don't know why, is you go here flux report and compute it from here, it will give you a problem. So to create that one, instead use new surface report and create the mass flow rate report, okay, and select the inlet. So print and plot standard, okay, so in my case are just print and plot, okay, and then create this one. This is the average of the x velocity, okay. So you will go area weighted average, give it a name, print and plot velocity x, but you will need to apply it in a line where we're going to do the plotting, the sampling, and compare with experimental results. So let me show you that line, those coordinates, because you needed to create this one. So as you go into surfaces, right click new line, and you're going to create the line here. So let me give you the coordinates that I have it here. So these are the coordinates of that line. So it's a line here in the middle, okay? So let me show you now. Okay, let me again show you. You have it 0, 0, 0, 18, 0, 28 in Y and X. So let's plot it. Okay, see that is this line where we're going to do the sample. So you create that line and you go back here. So when you create is area weighted average, velocity x, and sample along that line. In my case is line 2, or probably you will have a different name, I don't know. So you just plot to screen and print to the console. Okay, have that information. So you will have this tree or any other that you would like. Okay, so your report definitions that you are plotting. Then let's add a converge condition. Okay. And remember that this will converge very, very smoothly, but put this one just to add the second one in this velocity. So we're computing that velocity. So add that converge condition in this velocity. Okay. And now we can initialize. So this is a case where usually when you have periodic conditions, hybrid initialization, this one, or the full multi-grid doesn't work. So you need to give uniform initialization. Okay, so here you have the values, but remember that this velocity, we can compute it from the mass flow. So in this case, the mass flow is 1.5. So you can get the estimate. You have the density. Okay, you need to know the area. When you're working in 1D, is per unit depth. So you just need to compute the area. So to compute the area, remember that you have the calculator reports, and you can get those integers. To enable, you need to put an initialization. Okay, it doesn't matter what you put there. So see that now you enable reports, and you have here surface integral. So as you go here, you select the inlet, compute, this is your area. Okay, so now using this area, you know the density, okay, and the mass flow is 1.5, you can get the velocity. Okay, so that computation, okay, will give you this velocity. Okay, 25 is moving in this direction. Okay, then 0, and then probably here you will have different values. I think you will have 1, 1. Okay, so usually here you know how to compute the estimate, but sometimes when you are lost, usually this is a good choice. Okay, 0, 1, 10, 10, 10, 10,000. Okay, so you recall this is a well resolved mesh, so usually omega is a large value. Okay, see that this is well resolved, so it will be large value. Okay, so let's put this value, and we have our definition. Initialize. Okay, remember every now and then save your data, and we can run. Okay, so see that by default here you have 1, and I'm going to show you something here that this controls. Okay, this is pseudo transient, so here you have somehow the time is entering in your computation. Okay, and what is doing that each cell we have different time step. Okay, so when you have fully unsteady, is a global time step. So the smallest cell, okay, is the one that is going to control your simulation, the CFL number, with the CFL number. Here, when you do pseudo transient, each cell will have different CFL numbers. Okay, it's a huge violation of physical principles, but you can reach steady solutions, okay, fast and in a more stable way than using a fully simple pressure velocity coupling, the simple or simple C. Okay, why? Because now you are adding time. You have, besides on the relaxation, you have also time. So this is what it's doing, is controlling. So the larger means larger CFL or larger time step. So first let's run with a time scale factor of 1. Okay, and then we're going to play around to see how the influence that have in converging to the solution, let's say the ideal solution fast. So we can press calculate and see that you're going to start to have your velocity X, mass flow, your Y plus, okay, a low value, your oscillations, and your scale residuals. Okay, all your quantities here, your second convergence, okay, report conditions. And as you leave this value, it will get to the solution, but it will take a really long time. See, that is converging really falling really slow. Okay, it will a long time, means like probably 2,000 iterations, if I will recall. So now let's go and let's increase this one. Again, as you decrease it, means smaller time step, more stability. Okay, but we want to go faster. So if I put 5 here, you will see a jump here. See that? Usually, like changing the time step, you are moving faster. The influence here in your residuals, and then you can iterate. So this is what you're doing. So this is like equivalent to changing time step. So usually you have to be careful, because 1 is the ideal value. Okay, so it will be like each cell would have a CFL number of 1. If you put it larger, okay, larger time steps, but you have to be careful, because sometimes you can destabilize your solution and can diverge. So it's not a good idea to put here 1000, but sometimes you can use it depending on your physics. Okay, so I see that in this case 272 it converge. Okay, but however I think I still see that the quantities is still oscillating a little bit, so I think it might be better to let's go in this converge conditions, or probably instead of this one let's reduce the residuals. Okay, so let me put 0.4, and now before let me increase it to 10. Okay, I know with 10 it will still work, and see that boom 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 boom, and it should be converging now. Okay, then it's measuring the other quantity. See that it is oscillating, and see that we have the target mass flow rate that I was telling you. Quantities is still oscillating a little bit. This is the one that where we put the control, and at this point let's wait a little bit. Okay, in my case it conversion is 647. Well, let's not say converge, but it satisfy these criterion that we set here and here. See that it might look like that it's still you need to let it run a little bit more just to get it more flat here. We need to flat this curve. Just talking about flattening curve in this time of a pandemic problem. So see that this one also still maybe you need to let it run a little bit more just to flatten. But let's just stop here because I think we can do already some validation and some comparison. So we studied the effect of this there here. So now let's sample the solutions. So, but before sampling, I want just to let you, okay, let me show you first my sampling. Okay, so see that what we have here, what I'm showing here is just two additional quantities. These are derived quantities. So see that the distance, I normalize it. See that it's 0, 1, and also the velocity is normalized, just to compare also with the experiment which is normalized. And just to show you also the experiment. So load the experimental data, and see that here we have large differences, probably here some agreement, but since that it can be improved, make it more flat in here. So how do we compute this new quantity, the custom function 1 and 0, and what there are? So those custom functions, you can compute it here. Okay, so you can define this after you finish the simulation or before, it doesn't matter. So as you go here, I will show you first what I have managed, and see that custom function 0 is this. So this is how I normalize that that distance, the radial distance. So let me go here and put it here, and then the custom function 2, this is how I normalize the velocity that I'm going to sample. Okay, so how do you create then? So as you go here, new, you go new, and you create those quantities here. So this is a little bit annoying, I hate it, because actually you cannot type there, you need to use the calculator, and then you can access everything from here. Okay, so see for instance, if we want to create this one, okay, we have it there, you just go in the calculator and you start to type. So parentheses, so let me move it. And then you put the square root, where do you have the square root? Here. Another parenthesis. Then you access x is the coordinates. So those, you get it in the mesh. X coordinate, press select. Power of 2. Plus, then y coordinate. Power of 2. Whoops. Del to delete, select, power of 2, close parenthesis, and then the other minus 0.2, close parenthesis, and this open, so this will be 0.5. So this is it will be outer radius minus inner radius. Okay, you give it a name if you want. So I will call this one banana 1. Define. And you create it. Okay, so close. As you go here, you should have it here. And then you can do the same with the other one. New. And this is this definition. So you go, so you have velocity, x component, select, times y component, coordinates, divide this. This is, remember, this is the monitor that we created, the report definition, to have the average velocity, so you can also access them here. So access that times this should be the maximum, the outer radius, and close here. And I will call it banana adama. Define. And we're done. So this is how you create those quantities. So if you would like to create, for instance, another vorticity, so you can go derivative, and 2D you have that the vorticity normal to, let's say, your screen will be, for instance, the V will be the X. Okay, will be the V dx. Okay, probably no, the okay will be this one. Will be this one minus the U dv dy. This one. Probably, I think. So this will be kind of the, I think the, I would call it like this. Probably I make an error, but you see that you can access everything there. So now that you create those quantities, we can plot it. Okay, so these are, you access those quantities here. Okay, so for instance, I create banana and banana 1. See that those that I just created, and then you can load and compare with your experimental. So let's save this data, right, because we are going to rerun. So I will call it sol1, and now we're going to rerun with the curvature correction. So okay, as usual, you can do some plotting. Okay, so here you have all your quantities, velocity, okay, pressure, everything. So your custom fields you can access there. So this was this normalized quantity, the other normalized velocity. Then this one, the one that created, yeah, it seems that it was okay. So at the walls you have the vorticity, okay. And then just to be sure, if I go vorticity magnitude, okay, yes, it's okay. Okay, so let's rerun and using the the curvature correction. Okay, so as you go here, the only thing that you need to enable, boom, break the theory, this, but usually this coefficient is okay. Here you have the coefficients. Again, I don't know what they call it, constants, because you can change it. So you enable, and you don't need to do anything else, okay, like the production limiter. You run in the usual way. So let's run from scratch. Let's start from scratch. And I will put here 20, because I think if it will work as well with 20 to reach a faster convergence. And let's see what we have. All these definitions also still valid. Launch. Okay, see that all your monitors, you have it there. And let's see when we have a condition where we meet all these criteria. Okay, I'm back. So here in almost 400 iterations, we have resolution. So see that the residuals are falling in a monotonic way. Very nice. See that it still maybe would be a good idea to let it run a little bit, but let's take it for granted that this is okay solution. So what we need to do, well, you can check your colors as you want. Okay, it's useful. So let's check velocity. Okay, that was okay, and you have everything. Okay, but we want to do the sampling here, those quantities. So if I plot that, we already see that there is a difference here. Okay, and probably a better profile if we load our previous solution where we already have the experimental data. So if plot, see that it's clear, a better solution. So see the influence that it has, this curvature correction. It gave you a better profile in the core. Then, well, here they have a disagreement, a little bit worse than the previous one, but I'm pretty sure that this can be improved by simple, and in this case, let me go back to the mesh. I'll probably put it here. Okay, so we're sampling here, and our problem here is towards here, but probably I think that problem can be improved by refining the mesh, adding more cells in this radial, in this stream flow direction. So probably you split this one by 3 or 4, and it might be give you a much better algorithm. So this is the idea, and this is this curvature correction. Okay, the most critical ones, as I told you, production limiter and curvature correction. When to use them is a little bit dependent on the case, a little bit experience, but my advice is that if you need them, don't use it, because they can go in detriment of your solution. So the next case that we're going to do in our tutorial, so after the lectures, is this one. So now here we have system vorticity. Okay, so this is a nice case. So if you want, you can start to work in that. So here you have the instruction what I want you to do. So you have this geometry, you can generate it. You have the dimensions here also, the drawing. So you use your software, do the mesh. Everything is not use the mesh I'm providing. So just give these conditions. So you know that here you will need to enable temperature. So just a few instructions, and then do all these plots. Try to do all these plots. So when I talk about system rotation, is this. So see that you have a strong vortex there, and this will have a strong influence. So if you go here and you plot here, instead here I'm showing velocity, but if you plot with and without curvature corrections, you will see that the one without curvature correction will produce more turbulent viscosity here. Okay, so that is the idea, that is the big correction. So try to reproduce this, but next time we're going to redo this case. You have the geometry here, or if you are feeling lazy, just go and download it. Also, if you want to do the mesh and you don't want to do the geometry, you have the CAD file there. Okay, I hope you enjoy it, and see you next time. Bye.